I think I just took it for the AP class.
Yeah, exactly. So what did they teach you at 7 a.m.? Let's see what they should have taught you. So real quickly, what is the definition of power? And then we're going to move into Bayesian hypothesis testing. We're going to escape this. But this is the whole Neyman-Pearson lemma thing. So the max likelihood ratio. So just as a quick review. So Neyman-Pearson. Hear people say this kind of often. Neyman-Pearsonians is a camp, of statistician. They're the ones that if P ducks alpha, reject. But kind of Fisher was advocating that, and Neyman-Pearson were trying to explain what it meant. So I don't think Neyman and Pearson set us astray. They were trying to explain something theoretically. Here's a fact. Neyman and Pearson never did this. The thing that people do. And so they took this as a permission slip to just not think too much. I'll tell you what what most people do if you've taken a Stat 101 S-type class, they almost train you into doing this. And then I'll tell you what you should do. And I do think power is an important concept. And if you're doing hypothesis testing without talking about power, you're not doing anything. You really aren't. So again, let me just remind you, if somebody walked in my office, hypothesis in hand, so theta belongs to a set, whatever, they've got some model, they're even willing to tell me what F is. So it's like it's like the classroom. I don't have to do any modeling. They give me a bunch of data, they've got all of that, I say keep it to yourself. So tell me what your type 1 error is. So they tell me their alpha level, they say it's 0.072. That's their magic number that they like. In their field, they're not 0.05ers. They really like to break out. So they're willing to deal with 7% type 1 error rates. I say I'm going to just take a second, I'm going to compute a uniform random number. So just keep in mind one of these statements, here's how you connect it. Under the null hypothesis, a p-value is uniformly distributed. That's a fact. We'll prove that on the upcoming homework. So I can go draw a uniform random number a slightly different way. I just punch into my computer, uniform. I get a random draw. That number is 0.04. What's the probability that that happened? So something less than 0.072 happened with chance, 7.2%. So I say reject your null hypothesis. They're like stoked. I can go write a paper. I've rejected something. This was a current thing in my field. Everybody believes this. And Scotland just drew a uniform random number. Keep in mind a p-value under the null hypothesis, all done under the Neyman-Pearson lemma, will give you a uniform random draw. Trouble is that the power is astonishingly low in that analysis. Let me tell you what the type 2 error rate is. The type 2 error rate is the complement of 7.2%. So roughly 93% type 2 error rate. If the alternative was true, would I have gotten that case right? I want to just say it that way so I don't go the wrong way. So did I reject the null inappropriately? So there's two different cases. If the null were true and I reject it, error. If the alternative was true and I don't reject, error. So the second type of error is the type 2 error rate. And one way that you can think about this, sometimes I'll teach it this way, is type 2 error is 1 minus the power. That's the most extreme value in the power curve in the alternative side. That is true. There's a whole spectrum of power. So for all possible hypotheses. So what we want to do is minimize the type 2 error rate. Maybe this is what Neyman and Pearson were saying. If p ducks alpha, maybe you want to construct a test in such a way that the type 2 error rate is minimized and the power is maximized. So the way I've done it, by just not looking at anything and drawing a uniform random number, I have the same type 1 error, but my power is really low. My type 2 error is really high, and you can kind of see that. So Neyman and Pearson proved that if you take the max over h naught, so theta in the null hypothesis set of the likelihood, divided by theta in the alternative set, I'll call it h1 just to match that, likelihood over x, and you threshold this by some c, and this c can be calibrated to a probability value. They're not numbers we know off the top of our head, but it would be akin to if your p-value is less than 0.05, we could calibrate the alpha level through this c. So this test right here has a fixed type 1 error rate. This is usually picked to fix the type 1 error rate, so it takes the place of alpha. It's not exactly, but there's a one-to-one correspondence. And there's a proof that says following this procedure leads to a uniformly most powerful test. So it has the minimal type 2 error. And that's cool. And so Neyman-Pearson said that's what Fisher's doing, and Fisher said, I'm not a sharp thresholder. I would treat a p-value of 0.04999 very similarly to a p-value of 0.0511000001. So you get the point. So those are close to each other. They say p-values are a continuum, and they should be treated continuously. And I sympathize with Fisher. I think that that's rational, but he didn't understand what was implied by his procedure. So 1 in 20 chance of rejecting the null inappropriately. What did he miss? Power. So he forgot to talk about that specifically, and Neyman-Pearson came through and said the p-values you should compute should come out of test statistics that come out of this ratio. So if you maximize this likelihood, maximize that likelihood, take the ratio, you'll get a certain implication on where does the data have to live for you to reject. So this describes a rejection region. So that's the whole idea. So this is uniformly most powerful. i.e. min type 2 error. Where is the type 2 error minimized for which hypotheses? All of them. That's what the uniform means. You know, across the whole spectrum of alternatives, because the alternatives live in a set as well. So that's the idea. Zach asked, okay, so what's power again? So it has to do with the type 2 error, but let's understand what a power curve is. So I think they teach this. Josiah, you teach this, right?
We don't teach power curves. We tell them power is the probability of rejecting a false null.
And you don't tell them what the full power curve is? Have them compute sample sizes to figure out what the power should be? That's a shame. If you teach one thing and you touch hypothesis testing, you should teach this. If this continues into the future that people don't understand it, it's not my fault. And it could not be your fault too. That's totally entirely up to you. I get the we part, but keep in mind I've given you liberty. So I think it should be taught because we don't want to teach people to do something robotic that's not sensible. And I get it, that's what they did in my undergrad too. They probably did it in yours. They're probably doing it right now. We could stop this, okay? This is what I think you should teach in the message you should send. So this can be done useful in a well-formed experiment, and it can tell you how much data you should collect so that you can balance the error rates. If you're only focused on p-ducking alpha, you're only interested in the type 1 error, that's all there is to it, and you haven't done what Neyman-Pearson really said to do, and Neyman-Pearson even tried to raise the truce flag and say, please stop, but no, it's just science. So I can do more science. What does that even mean? Let me just ask you a quick question. How do you get a small p-value? Increase the sample size. So if the alternative is true, which it almost guaranteed to be, it might just be off by epsilon from the null, it'll make your p-value gets smaller and smaller and gets bigger, you'll be able to detect that small difference in the null. That's the comment about practical significance and statistical significance. If we don't have something that's practical, why even teach it in the first place? This is my point. So you have to decide what that gap is, what a meaningful gap is, and the only way you can do that is through the power analysis.
Add some effect size in my comments.
Oh, okay. So in some roundabout way, you
Effect size and make them jack up a sample size and point out how if you jack up a sample size, any effect size.
So you talk about 2 points on the power curve and you compare them.
Yeah, in a sense, yeah.
Okay, cool. So you could even show the whole power curve. So I think people don't understand it in terms of formulas, but they might understand it in terms of a picture. I don't know if I did this in my grad theory class, because I kind of just expect everybody knows this, but I guess deep down I know that they don't. So let's just do it real quick. Let's consider a hypothesis. Oh, real quickly, what's the definition of power?
Probability of rejecting a false null.
Okay.
I'm going to say probability of rejecting the null hypothesis when in fact it's false.
Okay. That's the same thing. So I'm going to say it's the rejection probability of a false null. So important stuff. So it has to do with the probability of rejecting, and we're going to have to talk about what it means to be a false null. So let's just set up an example. Let's do it here. Example, xi's come from a normal distribution with mean mu, variance sigma squared, and I'm going to say that's known. If it's not, we'd run off to the t-test. Instead, we'll just do the thing that we were taught to do in pretty much any stat class. Let's just try to understand it a little bit better. So everything's IID. We know by now, instead of dealing with xi, the sufficient statistic is x bar. What that means, if I ran to Neyman-Pearson, the thing I wrote down here before, and I worked through the likelihoods, the only thing that's going to affect the shape of the likelihood is x bar. And that can be proven. So it's the only thing that appears next to mu in the likelihood is x bar. And we'll teach you theory on that in a more advanced class, but you could just demonstrate it that likelihood ratio, the only thing it depends on is x bar. So I'm just going to move to my sufficient statistic. That's x bar. Tells us everything we need to know. Know about mu. Tells you everything you need to know about mu except for mu. It's the most you can know from the data. That's what I mean to say. So just sum of the xi's over n. So you can go back to your 7th grade teacher and go, now I understand where x bar comes from.
What would be an example of an insufficient statistic in this scenario?
S squared.
Okay,
So
if you do the sum of the deviation from
Right.
x bar,
some of the xi squared, some of the xi cubed, some of the xi to the k power or k's not 1. All of those moments, the first moment has all the information and the other ones lose some information about it.
okay.
So S squared has lots of information about the variance though. So, yeah. The x1 doesn't have all the information about everything. I've thrown away a lot. So one data point is unbiased for mu, but I lost a lot of information. What is it doing? It's compressing your variance. So I'd like to think about what does the data mean? What is it giving us a signature of? That's what I think statisticians should think about. I've been unsuccessful there as well. So, okay, so x bar is the thing we know, so we can just kind of look at x bar. Here's the idea. If you did follow the Neyman-Pearson procedure, you would derive what you learned in Stat 101, that you do the z-test for testing all of this. Let me give you some hypotheses. H naught is mu is less than or equal to mu naught. Keep line to right theta. Mu is greater than mu naught. It is kind of important that that equal sign is on the null hypothesis. I will agree that when they teach this to you in Stat 101, they do that. That's the place where you can detect the most power on the boundary, of course, where mu naught is. What they really mean is this. But they want a condition on H naught, and in the classical paradigm, writing it down, what do you mean condition on a set? You plug a number in, you're maximizing over it. So this is the place where you have the most power to detect.
You want to put it back there as well.
Other way, yeah, of course I did that. So that's where that comes from. I like to write it down this way when we think about this as a Bayesian. This is what we're testing. So what we're going to do is we are going to draw our null distribution. We know what the distribution is because we know how the data came out of everything. So everything's normally distributed. What's the distribution of x bar? That's also normally distributed. Real quick, how do you prove that x bar is normally distributed if you know the x's are normally distributed? Give me one of 5 million techniques. It would give you the insight. I don't know if that's exactly, I would take that on a test. So, but I can kind of see it that way. I just work out the probability distribution of x bar and show that it's normal. So the likelihood's a different thing, and only because of symmetry would this work out well for you. But how do you find the probability distribution of x bar?
It's a linear combination of normals.
Yeah. So that's normal. How do you know that?
Normals are transformed, or well, under linear transformations.
How do you know that? How would you do it? They asked you to show x bar is normally distributed.
Sure.
Okay, that's a good sign for everybody else. Undergrad, hanging out, other undergrads? Sean?
Oh, I would just have a linear combination of normal.
Yeah, if you say that to me on a test, I'll accept it, but I want you to show it. Now I'm going to ask you to show your work. Brendan?
You can use moment generator.
MGFs will work. Perfect. So convolutional formulas will work, or just transformation of variables directly. They're all exactly the same thing. So, except the MGF is a little bit different. You have to apply this other thing, but I would probably run to the MGF. That one's easy enough to do. Okay. So we know that, we could show that as well. So what do I do? Where's the rejection region? Let me just ask real quickly. Should the rejection region, this thing is centered at mu naught. Right here. So this curve, that's the null distribution. Basically, I'm looking for the probability of my data and more extreme data. That's the definition of the p-value under the null hypothesis. So how did we compute the test statistic? We used Neyman-Pearson so we could be uniformly most powerful. You could have computed other test statistics and done worse. So Neyman-Pearson did teach us something that's valuable. So here's the null distribution. I'm going to be looking at x bar. So I'm looking at sigma over root n. And I want to know where x bar lives in this whole thing. Is this the more extreme region or is this the more extreme region? Which one is it? Anybody that doesn't teach an undergrad stat class right now? This is the whole stat 101 thing. Which way does it go? This contradiction thing, it's always backwards. So I'll tell you, it's either going to be here or it's going to be here. This is the one-sided test. In the two-sided test, it's both sides. So hands up for this is the more extreme region. Hands up that that's the more extreme region. Thank you. So, good. We're sensible. We're listening. We could do that. We passed our 101 class. Chase the tail direction. Chase the alternative direction. The alternative, the only place it's ever used is pointing us in what is the more extreme region. So it tells us what side of the p-value to look at. That's the only place they ever use it. The Bayesian will use this much more comprehensively. So that's this right here. What's this value? Right here. This might be the rejection region. So this might be my rejection threshold. And I might set this so that this is 0.05 area. So that's the 5% area. What is this number, just real quickly, since we're doing a review? What's that?
Which, like 1.96?
It's not 1.96, but it has something to do with 1.96. So let's just do it this way. So a lot of times what they teach you in AP, so is this, use the Z table, center it at 0 right here. So this is going to be normal 0, 1. So I'm going to do that standardization. My new test statistic is going to look like this. Z is X bar minus mu naught over sigma over root n. So that's the Z score that we're going to look at. We could show that that's mean 0, variance 1. We've only done linear transformations to it, so we didn't change the normality of everything. That's 1.96 right here. So when Z is equal to 1.96, I've got X bar minus mu naught over sigma over root n is equal to 1.96. So this is 1.96. This is sigma over root n. And then what do I add to it? Mu. So
Actually, I think I'm wrong. Wouldn't it be 1.6 something? Because it would be 2.5.
Oh, you're right.
It would be 1.68 or something.
68.
Yeah.
I did the 1.96 comes from the 2.5%. Thank you. Yeah, exactly. We mess up Stat 101 all the time. 1.68. Do you remember them all? It's like 2.57 is another one.
Yeah, I think that's
Crazy. How can we store that? So 1.68. Thank you. 2.5% is 1.96, and it's not even exact, you know. So 1.68 right here, and so this is going to be mu naught plus that thing. So that's that threshold. Sigma over root n plus mu naught. So this is shifted over here. Question is did X bar fall into this area? So this is the rejection region. You have a 5% chance of falling in there if the null was true. That's the idea. So that's the type 1 error right here. So if X bar is in here, we'll reject. That's all Neyman-Pearson. They told us to use this distribution, this test statistic. In Stat 101 or AP, they probably just handed it to you and said because. And I guess I accept that. You can't teach them everything all at once. But there's more to it. So I think we should just start out with the harder concept, teach them what power is, and then tell them this one is the best one. They'll teach it to you in college. Something like that. I don't believe in lying. So I felt like I got lied to a few times in there. So, okay, so we got all of that. We've got our critical value right here. I'm just going to call it star now, but we know how to compute it. So that's our rejection region under the null. Now let's think about the alternative hypothesis. So this is where the power is being concerned, right here. So if I look at the alternative, then I can pick values on the alternative. I'm going to pick this value right here. I'm going to call this H1. And I'm going to do the subscript thing. This is H11. So this is my first one. I'm going to do this multiple times. So this is H11. This is one value from this set right here. And in fact, I'm going to consider the whole continuum. I'm not even going to limit to myself to this. I'm going to see what happens on this side of the space as well and just compute the full power curve. So I can do it on both sides, or I could concern myself just with the alternative side, but I can do this over the whole spectrum. I'm going to build my null distribution if this alternative, this specific alternative value is true. So what I should be doing is drawing a distribution that looks the same. So that's supposed to look exactly like this other distribution, but it's shifted. So we're just testing the mean. So this thing is right here. What I'm going to do is I'm going to compute now under this curve, what's that probability? So this is the probability of falling in the rejection region under my alternative curve. So now I have this probability, which is bigger than 0.05. So it's some value. So what I'm going to do is I'm going to draw a curve. I'll label mu naught. I just picked a value. We know that this one right here is 0.05. Maybe I made that too big. Let's do at mu naught, this curve is 0.05, which means that if I stack this distribution right on top of this other one, what's the probability I'd fall into the rejection region? It's 0.05. So that happens right here. And over at this new point that I just consider h11, I get some other value, and it's bigger than 0.05. Now I can take this distribution, this alternative distribution, and ask the question, what if the alternative is over here? So that specific value, and I can redraw this again. So I pick a new value. Let's just pick it here. Pretty close. And I can keep moving this thing over, and I'll get a slightly bigger value right there. And anytime that I push this to the right, it's going to be increasing. And if I slide it even all the way past mu naught, it's going to be going down. And it's going to do it in a monotonic fashion. So the one-sided test makes sense. It's got a one-sided bound, and this is a monotone power curve. Lots of good things happen there. This looks like this. So this is over all of mu right here, and this asymptotes to 1. So this is what I'm going to speculate Josiah teaches. He says, grab me a point right here. He's going to talk about this distance right here, and he's going to ask the question, what does n have to be if I want that to be big? So he might pick this to be 90%, and I want that to be 0.05. And then you solve for n, and that's your sample size calculation. So if you ever come to a statistician and they say, can you do sample size calculations for me? They heckle in the back and they go, give us 3 weeks, we'll do it for you. And we'll give you an n in a minute, and you're going to put us down for $10 million of your grant because we told you precisely which n to use. They're doing this. They might have a modeling difficulty if they don't know everything's normal, but a lot of times they're just doing this. Sam?
Oh yeah, I was just going to say that isn't this curve just a flipped CDF curve where we're plugging in?
Yeah, but it means something to us.
Right.
It is adding probabilities. It looks like a CDF. That is what they look like. But this one means something special to us. It's been centered a certain way. The slope of it is a certain way. All of that thing means something to us. But yeah, it looks like a normal CDF. So absolutely.
But I could think of it that way.
Yeah, you can if you want. I mean, you're computing this area, and that is the normal CDF function. And you're just adding those things up. You can. I just don't think of it as any old normal CDF. This is telling me about the probability of rejecting under different scenarios. So my interpretation of this specific CDF is special. So I don't want to take off the part that it's a special one. And I think this is what we need to be teaching if we even touch hypothesis testing. We need to touch this question of what would the probability of rejecting be if H1 was way over here. If this is tiny, then what are we doing, you know? So we want to be able to reject quickly and say something about what would have happened under these different scenarios. This is the way you account for the alternative. And I think you have to account for the alternative.
So just going back to the sample size thing, is it like as you move over, you get a larger sample size on the curve?
You have a fixed sample size.
Oh, you have a fixed sample size.
So you fix the sample size, and then you can ask questions. If I wanted this right here to be 0.9 and I wanted this right here to be 0.05, you know, it doesn't look that way in my picture. I could ask what is the sample size for it to do that with this effect size right in here,
Okay.
that difference. So what that's telling you is you're able to detect that difference very well. And so you're calibrating that your ability to detect that difference, if it's true, is high. And I think if you do not do this, you're no frequentist, you're no Neyman-Pearsonian, you're not a statistician, you are just turning a crank, you are the next robot. So it is the worst thing that we have done to all of statistics is we've let people not compute this curve. So again, I can just draw a uniform random number without looking at anything if I just want to consider the type 1 here. So it's not just this magic crank for us, it means something. And I think this is what Neyman-Pearson and Wald were advocating. So Wald came in and said, you have to do all this, you have to do all this. Maybe he just didn't say it the right way or something, but the only time I hear people talk about power, and this is almost true and it's sad, is when they don't detect, they don't get a small p-value, then they say, well, I guess probably the power was low. So then they go out and get a larger sample size. Here's what will happen if you don't have a real rule for when to stop in this game and you just say, I'm gonna go get n bigger and bigger and bigger. If the null was true, that's a uniform random draw. Obviously they're in any position, any n, they're uniformly distributed, but obviously they're correlated if you're just adding in more data. So, but at any point, that p-value is uniformly distributed for any n. So you're just drawing uniform random numbers until it ducks alpha. And that will happen. You know, how long do you have to wait for it to happen? You could even compute that. If the alternative was true, then the p-value will be coming down. The question is how fast does the p-value cascade? And that's what the homework is about. And I want you to just look at that, and as the hypothesis gets more and more ridiculous, the rate of the p-value's descension is getting faster and faster. So that's kind of a roundabout way of thinking about power. I don't want to test on that because then you'd have to test on what's the rate, did it, you know. So I think I sympathize with Fisher that things probably, unless you're doing a well-designed experiment and you have n up front and you've calibrated the power, and you have a sample size calibration to that, it's just a game, it's not science. So, okay, let's talk about what Bayesians do. It's not all good news either. I do think there is good news if we do the right thing, it's sensible. I understand conflicts of interest. So, let's think about what a Bayesian does. So last time I introduced you to the Bayes factor, I want to tell you a little bit more about it. It's very similar to the max likelihood ratio. And if the likelihoods are very compact, low variability in them, the max likelihood ratio and the Bayes factor will be very similar to each other. So the Bayes factor is this. I'm just going to write it out this way, likelihood theta given x. If you did drop the sampling distribution in there, remember you're touching the parameters, so you're treating it like a likelihood. All the normalizing constants will cancel in the ratio. So this is going to be the integrated likelihood, but I'm going to concern myself to the two sets, so to the two spaces. So let's just write down our notation. Again, theta is less than theta naught, or let's just talk about theta is an element of h naught. I'm going to write it down like that. Let me do this. Let me actually give us a prior on h naught. And this is, I'm going to write down like this. I think this is the notation we used last time. So I'm going to have a prior on h1. And I'm just going to write it down like this. And this is for all thetas an element of H naught. This is theta as an element of all the alternatives. So I'm going to integrate this with respect to the null hypothesis. And I'm going to integrate this one with respect to the alternative hypothesis. And we talked about these priors last time, and they're basically, how do you smear mass across the hypotheses? How much weight do you want to put on the virtual values in that set? So for the point null, there was only one way to do it. So, and then we had to be really concerned, I told you, be very, very careful in how you treat the alternative. And we're going to analyze that on Friday. How we actually look at it and what matters. We'll do the calculation. We'll write it down analytically and see what matters in the calculation. I think it's a fun exercise. But this is the Bayes factor. So instead of maximizing over the likelihoods over their different sets, you're averaging over those two different sets. So it's a different way of comparing likelihoods. The average likelihood in some sense in the null set compared to the average likelihood in some sense in the alternative set. So that's what the Bayes factor is, and we'll start to understand properties of this creature. I've only told you a little bit of the story. Let me write this down slightly differently. If you'd like to write down like this, sometimes I like to do that. This is the sampling distribution. It's the exact same formula that we'd be plugging in right here. We just think about them different. So the notation is just a different thing. I'm operating on theta, so it's a likelihood to me, but it might be easier to see this if I give slightly different notation of these things. I'm going to call this my prior on theta, given the null hypothesis. So again, how I've smeared mass over the null. And this is, again, how I've smeared mass all the alternative. So I just want to operate using Bayes' theorem in the way that we're familiar with. So if I just wrote it down like this, and I wrote down this thing as a ratio, I might be inclined to just write this down. So that's what the Bayes factor is. And some people will interpret it this way. This is just the ratio of marginal distributions under the null compared to the marginal distribution of the data under the alternative. So this is just the ratio of margins, the data margins. So in some way I interpret this as how well does the data fit the null hypothesis compared to how well does the data fit the alternative hypothesis. And if I were to interpret the max likelihood ratio, I'd be inclined to say exactly the same thing. So my definition of fit is slightly different. My mechanism for measuring fit is different. But it's the same idea, it's just how well does the margin fit. But the Bayesian has that exactly right because they've marginalized out theta.
So it's kind of similar just like a penalized to a ratio of penalized likelihoods, except that we're integrating.
I think so.
It's very similar to a likelihood ratio.
That's all it is. That's all Bayes is. So penalized likelihoods. And there's different reasons for penalizing the likelihood. And we get different properties out of our analyses by penalizing likelihoods differently. If we didn't say our prior assumption, and we said it like that 50 years ago, we probably wouldn't fight so much. So, yeah, exactly. I like saying it that way too. So that's the Bayes factor. Another way to write the Bayes factor, and I think this is a little bit more obvious now, but I need to tell you about the total prior. So I've got the priors compartmentalized to their conditional hypothesis sets, but I want to tell you about the total prior on theta. So just remember this conversation we had last time where I drew out some hypotheses where I said maybe this was the sharp test and I placed mass on that. And then on the alternative space, theta is equal to theta naught versus the alternative theta is not theta naught, so probably the most ridiculous question to ask in all of statistics, but people do it anyway. We're going to answer this question, show what a Bayesian says about it, and see the relative advantages and disadvantages. There's both, just like anything. So I drew a picture like this, and I said, well, maybe we would build a prior that looks something like this, and I'd make it maybe normally distributed. I want to center them at the same place. So I've got a point mass on the null, and I've got a spectrum on the alternative. And if you want to remove that one little point, because I said the sets can't overlap, you remove it. And if you leave that point right in there, it will not make a difference in your calculation. We've all taken calculus. So, but you can subtract that out of the set. So I might use the conjugate prior right here, and we'll look at it and see how well it performs, talk about issues. Not all good news, not all bad news. But I didn't tell you about the relative heights of these curves yet. So I could put more influence on this and drag it up. And I can put more influence on this curve or less influence and drag them up or down relative to each other, but basically have the same shapes in everything. And so I need to consider my prior distribution on H naught itself. This is a number. And the prior distribution on the alternative, this is also a number, and it's 1 minus P R H naught. I'm going to give this some notation. I'm going to call this pi naught, and I'm going to call this 1 minus pi naught. So I need to place those masses on the hypotheses. Now I will say, of course, if you have two competing hypotheses and you say something like the prior distribution, my prior mass that I'm placing on the null is 0.999999, and the posterior probability of the null is 0.9, it's really high, it actually went down relative to your prior, it means that the data is supporting the alternative more. So make sure you pick these rather objectively. If I had two competing hypotheses, I'd be inclined to say this number is 1/2 and 1/2. I'm going to place equal weight on each one. So a lot of people will pick on this in the analysis and ask, how did you pick that? It's actually not the most important thing. The alternative variance is much more important, and we'll see that in a couple examples. But our total prior on theta is just this. So pi theta is equal to pi theta H naught. I'm going to write it like that, times pi naught. Let me actually stick this in front. Pi naught plus 1 minus pi naught pi H1 theta. And if you want to see Bayes' theorem in there, in here, this is pi theta H naught times pi H naught. So that's that, that's that. So all I'm doing is marginalizing over the hypothesis set. So I'm just left with a distribution on theta. If we were doing the point mass prior on everything, this prior would look like this. So this is called a point mass mixture prior when we test the sharp case. I haven't been specific. This is always true, and this will work over any hypothesis sets so long as they're not overlapping each other. I think that makes sense. So here's another way to write the Bayes factor. I can look at the posterior probability of the null, and I'll use PR because this is a probability, because the null is a thing. It's a discrete thing. This is the posterior probability of the null given the data. If it were the normal case, I'd just be conditioning on X bar, divided by the posterior probability of the null, of the alternative given X, divided by probability H naught divided by probability alternative. So oftentimes I write this like this. Pi naught over 1 minus pi naught. And you can see that if you just stare at this right here. So how do I get this thing in the first place? That's just f of x given h naught times pi naught divided by f of x, the margin on the data, over the total prior. So this margin on the data isn't conditioned on h naught, this is over the total prior, where I've integrated this. This margin on the data appears here as well. Just be super specific. F of x given h1. How do we do this? We computed an integral. So this is 1 minus pi naught over the margin on x. So those f of x's cancel each other. The pi naughts cancel each other with that, and vice versa. So this is an interesting way of thinking about a Bayes factor. So I can think about it as this marginal fit of the data on the different hypotheses. Sometimes you'll hear people talk about this description of it, and they'll say how the posterior odds changes compared to the prior odds. So it's the odds of the posterior odds to the prior odds. So I'm looking at how well the data supports the odds in favor of the null a posteriori compared to how I thought about it a priori. So how did my data change the way I thought? So that's one way to think about it. Trouble with Bayes factors is that they live between 0 and infinity, and I have a really hard time thinking about that. So if somebody tells me, well, the Bayes factor is 600, well, that's huge, right? I don't know. So we're not used to thinking about that scale. Sometimes people will give you thresholds on how big the Bayes factors have to be for you to think that there's moderate evidence in favor of the null, strong evidence, and you'll see this tabled for you sometimes. Those numbers come from this formula. So I can relate the Bayes factor to the posterior probability of the null. So this looks like this. Probability of h naught given the data. And this is what a Bayesian thinks about. This is what a p-value is not. There is a little bit of confusion because for the one-sided normal test, if I use the flat prior on everything, and we'll talk about that, if I'm doing the one-sided test, if that's fair game, this posterior probability is that p-value. If you go to the sharp test, the more common test that most people do, that sharp test p-value and this posterior probability will never agree with each other. I don't care. If you ever told me that the posterior and the p-value turned out to be the same in that test, I'll call you out. I've never seen it. They're so wildly different from each other. So we will study that case in detail tomorrow, and then when we come back from the break. This looks like this. 1 plus 1 minus pi naught over pi naught, where these are the prior odds, times the Bayes factor, inverse, all inverted. And we can rewrite this. I could go through a lot of algebra. Let me just rewrite what this actually looks like at the end of the day. Remember what the Bayes factor is? It's the margins. It's f of x given theta naughts compared to f of x given h naught in h1. So this is the marginal probabilities. You can rewrite this like this. This Bayes factor is f of x given h naught, f of x given h1. So I haven't inverted it. The inverse is just flipping it upside down. So you can see this H1 goes next to that right here. This is just Bayes' theorem in disguise. So just a little bit of AP algebra, maybe not even that. So you could show that. I think I'll refrain from doing it since we're 1 minute over. This is the way I usually like to think about things. If you look at my literature, there's one paper where I didn't feel like computing the Bayes factors. It was just too horrendous. And I ended up saying the likelihoods were relatively tight. I maximized, I used the maximum likelihood ratio, and I used a bound on the Bayes factor, and I was able to bound the Bayes factor. So the maximum likelihood ratio does bound the Bayes factor. We'll see that either next time or when we come back from break. So there is a correspondence between the two things. But it also tells us that Bayesian decisions are bounded in some way by Neyman-Pearsonian decisions. And we'll see what that bound implies. And so it's rather interesting. But these are just different ways that you can think about the same concept. So the posterior odds compared to the prior odds, the marginal fit of the data, so on and so forth. We're going to start studying different hypothesis test types. We'll look at the one-sided test next time when we come in. For normal, this posterior probability matches the p-value. You actually don't have to go through all of this work to compute this, and I'll show you some easier ways to do it. But when you get to the sharp test, the point compared to the spectrum, you have to do this. So there are easier shortcuts for tests, but this will always work. So I basically told you everything in general, and now I need to show you examples. Okay, I'll see you guys on Friday.